to Chapter 2.1, Significant Digits and Scientific Notation. So first off, let's start off by talking about significant digits. So significant digits are a way of measuring how accurate you know your number to be. So let's start off with an example, such as measuring a spoonful of sugar. You can measure it to be 2 grams. That has one significant digit, easy to see because it's only one number. You can measure it again with a more precise way of measuring and know that that spoonful has 2.1 grams. That's 2 significant digits. I just shortened it to say sigdig because it's a lot faster than writing out significant digits. You can also measure it with an actual, more precise scale like the ones we use in a chemistry lab and get 2.18 grams. That would be 3 significant digits. If you measure it with an even more advanced scale, it would be 2.183 grams, which is 4 significant digits. So there are some rules to knowing which digits are significant. The first rule is all non-zero digits in a number are significant. So if we have a number such as 3.86, each one of these digits is significant, so we keep them all. The second rule is all zeros before a non-zero digit are not significant. So in our example, 0.0089, these 3 zeros are not significant. The only ones that are significant are these 2 numbers. These zeros are just placeholders because they can't write 89 and expect you to understand that it means 0.0089. It's not the same thing. Last rule is all zeros after a non-zero digit are significant except when placed at the end of a whole number. So one example would be 0.203610. These 2 digits are significant because this number would be different if I removed that 0, and this 0 is required at the end to tell you that I've actually measured it to a higher degree of accuracy. If we take a look at 10 in 3 different ways, you'll see 3 different significant digits appear. So over here, this is only one significant digit. It's only one because it follows the third rule. All zeros after a non-zero digit are significant except when placed at the end of a whole number. So this 0 has to be placed there because if I don't put it, then you'll think it's 1. Over here I wrote 10 decimal. If I went to the effort of writing that decimal, it must mean that that 0 is significant. Lastly, we have 10.0. That 0 at the end is also significant because if I went through the effort of writing a 0, it must mean something. So because it's after the whole number, it's significant. Next off, let's talk about rounding. So over here I've drawn a very nice triangle, and we're going to try to measure the area of the triangle and correctly round. So as you can see, the height is 22 centimeters, and the base is 19.5 centimeters. The equation for the area of a triangle is area equals base times height divided by 2. So 19.5 is the base, 22 is the height. That gives us 214.5 centimeters squared. So if you look at our 2 numbers, this one has 2 significant digits, this one has 3 significant digits. Somehow though, we're more sure of our final answer than we were of the 2 initial measurements. That's not possible because our final answer can only be as accurate as our initial readings. So over here, 4 significant digits can't possibly be correct. The actual answer is 210 centimeters squared. This is the correct answer. Even though mathematically, yes, this is correct, but because of our readings, we know that this is the more precise answer. There are two rules for rounding. The first one is if you're adding or subtracting. So when you're adding or subtracting, you need to use the lowest number of decimal places. But if you're multiplying or dividing, you use the lowest number of significant digits. Over here, we were multiplying base and height and then dividing it by 2. Base has 3 significant digits, 19.5, so 1, 9, and 5 are all significant, and height has 2 significant digits, both of the 2's. So, following rule 2, we need to use the lowest number of significant digits, so that would be these 2 right here. I have that 0, remember again from before, that 0 is not significant. If I left that out, it would mean 21, which would be completely wrong. So just 2 quick examples. So when we're adding or subtracting, such as the case with 6.0 plus 3.04, the answer is not 9.04, even though mathematically that is correct. If we round properly, it should be 9.0 because the lowest number of decimal places is only 1 decimal place. So right there. We're here, if we have 3 times 7.1, it's not 21.3, which is the actual mathematical answer because that has the wrong number of digits. It's not 21 either because Rule 2 says use the lowest number of significant digits of the initial values, so 3 only has one significant digit. So when you actually work it out, it's 20 because only that 2 is significant. So lastly, we're going to talk about scientific notation. So scientific notation is useful when you have very big or very small numbers. So over here I wrote a very big number, right, as 68 million billion. So nobody goes around talking like that in the scientific community, so we have a shorthand of writing it. So the shorthand notation would look something like this. 6.8 times 10 to the 13th. So this 10 to the 13 tells you how many zeros there are after. So it's faster to write number 1. It took me forever to write this, 2 seconds to write that. Also, it tells you the number of significant digits unambiguously. Remember from earlier in the video, you should know that this only has 2 significant digits, but if you're a little confused still, this unambiguously tells you you have 2 significant digits. So how do we go about doing it? So first, we find the decimal point. Over here, because this is a whole number, the decimal is at the very end. So when we find the decimal, we just count the number of spaces between the decimal to the whole number. So that would be 1, 2, 3, 4, 5, 6, 7, 8. So we can just write that as 2.83 times 10 to the 8. The important thing to remember though is that you need to keep all significant digits in your whole number. I've written a couple of examples right here. 0.004710 can be rewritten as, well, if we take the decimal place to be over here, because it's a decimal number, it's over here. We go 1, 2, 3. So 4.17 times 10 to the negative 3. Notice how it's negative over here because we have to go the opposite direction. Negative numbers in the exponent denotes a small number, whereas a positive number denotes a large number. So over here we have 17048, which we can just write as 1.7048 times 10 to the negative 4, because if the decimal is over here, we go 1, 2, 3, 4. And because we're going to the left, it's a positive number, whereas up here, when we were going to the right, it's a negative number in the exponent. Over here, I've written a number in scientific notation, so it's 3.28 times 10 to the 7. So if we want to go backwards, you just write 3.28, and you keep moving the zeros. So 3.28, the decimal is over here. We go 1, 2, 3, 4, 5, 6, 7, and the decimal is now over here. So that's how you can interconvert between the two forms.